Solutions to the Forrest's homework problem at set 1, which really is all those ones on that page. I think that was a little unclear. They just happen to be from two different parts on the physics classroom. Pardon my voice, I do have a cold, so hopefully I won't be coughing too much during this. Problem number 1 is pretty easy. It's basically just weight equals mg, which is a version of Newton's second law, F equals m times a. So on Earth, the elephant has a weight of 58,800 newtons. On the moon, we just divide that by 6, so that's 9,800 newtons. For problem 6, in this particular case, it's a really straightforward Newton's second law problem. The key is, in order to figure out the net force, you need the total mass. And the person in the little car he was in had the same mass, so we add those together. So that's 73,800 newtons. For problem 14, I hope Chinedu appreciated the fact that I used a name, so that's fine. He does have a little sister. So I drew the free body diagram out here. The net force is simply the difference between the applied and the friction forces because the vertical forces are balanced. Excuse me. So to find the mass of the situation, I need to take the weight divided by 9.8, so that's this formula again, and I get 31 kilograms of mass. So now to find the acceleration, I use the 28 newtons of net force and the 31 kilograms of mass. Pardon me. And that gets my acceleration. Problem 17. I drew a free body diagram for this. So it says that force of air resistance is 118 newtons. When I figure out the gravitational force, mg, 808 newtons. So to figure out the acceleration, I use net force over m system. So acceleration around 8.4 meters per second squared. For problem 21, this is similar to an example I did in class. The rocket's got a mass of 0.104 kilograms. It's accelerating upward at 45.9 meters per second squared. So essentially, if I know the mass and acceleration, I can find the net force. But that net force is caused by the thrust acting upward and gravity acting downward. So I'm separating this into two separate forces, because my goal is to find the thrust. So the thrust is up, gravity, which is basically this is m times g again, is down, and that equals the net force, which is the mass times acceleration. So we get the thrust minus 1.02 is equal to 4.77, so the thrust is 5.79 newtons. For problem 26, this is, again, I drew a free body diagram here. Friction, push, normal, and gravity. First thing I'm going to do is figure out the gravitational force, which is 823. That's m times g again. Therefore, on a level surface, the normal force, also 823 newtons. So therefore, knowing that helps me figure out the friction. So you're given the coefficient of friction. You just figured out the normal force. So friction is 288 newtons. So now to figure out the force of the push, I go back to Newton's second law. Much like the last problem, I separate the forces, so push minus friction. I know the friction amount, I know the mass of the system, I know the acceleration of the system. So I get push minus 288 equals 101, so the push is 389 newtons. Going to the second part of these, problem 2, just a simple vector force looking at horizontal and vertical components. Hopefully you are in degree mode. Problem 6, I need to set up a t-chart to figure out the net force. So I end up with 76 newtons down, 174 newtons to the right. I redrew that. I use Pythagorean theorem and inverse tangent to get the amount, the resultant in the angle. So that's 90 newtons at 24 degrees south of east. And then for part B, I ended up getting the acceleration based on force over mass. The mass was given you in part B. So same angle, just the net force divided by the mass. So really this was more of a vector problem than a force problem. Problem 13 is similar to what I did in class as an example. So I'm thinking here, big idea, the force up equals the force down. Or I could say force up minus force down equals 0. This wasn't an oops, by the way. I did this first because it was a short problem, and the next one's a long problem. So each string has the tension, which is going to be the same because the angle is the same, times the sine of 34.5 degrees as its upward component. So I have 2t sine 34.5 degrees as the upward force. mg is the downward force, which is shown up here. So I end up getting tension is 373 newtons. For problem number 9, so this is a tough one. You're trying to figure out the acceleration of the crate. But in this case, you're pulling up at an angle. What that means is, in this case, the normal force will not equal the gravitational force. So I do need to think about both horizontal and vertical parts when it comes to this. And I showed over here in these circled parts kind of my order of doing things. I was given the mass, I could figure out the weight from that, and I was given the coefficient of friction. So to determine the answer, I need to split this into components. And then I know that, so 692 sine of 36 degrees is 407 newtons up, 692 cosine of 36 degrees is 560 newtons over. And I get the normal force plus 407, that's my upward forces, and that equals gravity down. So in other words, this normal force is going to be less than the force of gravity down because I'm already at pulling up with 470 newtons as found by this. So therefore the normal force is 691 newtons. The next thing I want to do is figure out the force of friction. Well, the force of friction is coefficient of friction times the normal force. And notice that's 0.548 times 691, not 0.548 times 1098. Because, again, these are not equal this time. Next, find the frictional force. So if I got, next find the net force, pardon me. So now I need to think horizontally. I know that the vertical net force is 0 because this thing isn't leaving the ground. But horizontally, I have friction going to the left and the horizontal component of the pole going to the right. So the horizontal force of the pole is 560 newtons. The force of friction I just found is 378.7 newtons, so that comes out to 181 newtons is the net force. And now I use Newton's second law to get the acceleration. So hopefully going over those help. There is no one set way to do any of these problems. You do almost always come back to Newton's second law at some point, but you've got to take a lot of things into account. Thanks.